Hi, my name is Juri Opitz and I'm happy to talk with you about AMR quality rating with a lightweight convolutional neural network. But first, AMR. What does that acronym actually stand for? Well, it stands for Abstract Meaning Representation, and the goal of it is to capture the meaning of a sentence in a structured graph format. Here in this example, we have the AMR graph to capture the question, does a small cat drink milk? And here we see the root of the graph, which is the main predicate. It's drink, and you can look its exact meaning or sense up in the proposition bank. What we also see is that cat is the agent of drink, arg 0, and milk is the patient of drink. And we see that AMR also captures other things, such as speaker mode. In this case, it's interrogative. Currently, AMRs are being leveraged for more and more tasks. For example, they have been shown to help neural machine translation, summarization, question answering, and more tasks. But there's the question, how do we obtain these graphs? And well, we do this by using AMR parsers, which are automatic systems that convert natural language sentences into these AMR graphs. However, there is a problem with this. Namely, because the task is so complex, the parsers are often deficient, and these deficiencies can be very hard to detect. Here's an example. This is the parse of a neural parser of the sentence, a group of scouts are hiking through the grass. And immediately we see that this node it must be kind of false, because grassroot, well, there is no grassroot movement going on here. But there are also other flaws which are much more hard to detect. For example, when we look the main predicate, hike, up in the prop bank to see what it actually means, we see that hike causes something to move. And we have the arg 0, it's the agent of hike, and the arg 1, it's the patient of hike, the thing being moved. And here we see that group, it's the arg 1 of hike in this parse. So actually this parse says that the group is being moved, so which is wrong, because the group is actually the thing which does the activity of hiking, so it's the agent of hike. So this parse, it actually reflects a meaning more like that a group of scouts are moved in a grassroots movement, which is a bit weird at best, but does not reflect the meaning of the original sentence. That's clear. So to have the meaning better reflected, we would have to replace this node with grass. Hike should have another sense. Group should be the arg 0 of hike, and grass should not be the manner of hike, but the arg 2, the location where the hiking takes place. So here's an intermediate conclusion. AMR deficiencies may jeopardize AMR usefulness in application tasks by endangering the preservation of meaning, for example by leaving out meaning or by adding meaning deviations that are hard to identify. But if we could accurately and quickly rate AMR quality with automatic systems, we believe that we could signal downstream task systems the trustworthiness of parsers. We could select among parsers from different candidate systems, choosing the most trustworthy one, or we could help in semi-automatic annotation of AMR graph banks by letting humans only correct the most flawed parsers, or to let the system serve as an additional sanity check, cheap sanity check of human annotations. So this is our problem formulation. Traditionally, the quality of an AMR graph is assessed by comparison against the gold graph. But there's a problem with that, and that's that this process is very costly, because the manual creation of a gold graph takes on average 10 minutes per sentence. And we want to approximate this process and make it much cheaper by predicting an estimated quality based only on the sentence and the automatic AMR graph. Here's our model outline. We have the sentence and we have the automatic AMR graph. First, we convert the sentence into a dependency tree, and we do this to exploit useful similarities between dependency tree and AMR graph, which have also been noted already by other people. And we encode these two graph structures into vectors. We join this vector and perform regression on the joint representation to predict the estimated AMR graph quality. That is SMATCH. It's the expected triple match ratio with the hidden gold graph, and we can also assess other meaning facets, such as the negation quality of the AMR graph, or the expected coreference quality, or the expected word-sense disambiguation quality. But we have to develop a graph encoder for this. And so far, for this, two main AMR encoding approaches exist. Well, we can treat the AMR graph as a linear string and use sequence encoders, which is very simple but surprisingly very effective. Here's an example of the AMR or the sentence, the baby sleeps well. It's represented on one line and can be processed, for example, with an LSTM. Or we can treat the AMR graph as what it actually is. It's a graph, a set of vertices and edges, or equivalently a collection of triples, and use a graph neural network to encode it. But in our work, we ask ourselves, how do humans actually inspect AMR graphs? Maybe we could learn something from that. Well, what's pleasant for the eye is the AMR as a graph visualization. Here we have the baby sleeps well as a little graph, and this is nice for little graphs, but it depends on an arrangement algorithm that places the edges and the nodes, and it's not clear how to process this with computers. And if the AMR graph gets more complex because the sentence is more complex or longer, we might, depending on the arrangement algorithm, we might quickly get lost in a jungle of nodes and edges. So we propose to inspect a multiline penman string, and these representations are equivalent. So we have the graph on the left hand, and we have the multiline penman string representation of the R on the right hand, which uses indents and multiple lines to provide a clearer structure of the graph. And we see here that it doesn't need brackets, it's structure preserving, it's compact, it's formally well defined, and it's used by human AMR annotators in SAM banking and the AMR annotation tool. And what we exploit in this work is that this allows a spatial interpretation, which we see here. We project this multiline penman string representation onto a grid and add latent channels and say that this is something like an AMR image, which models a bit like the human annotator looks onto AMR graphs. Here's an example. This is the sentence, perhaps the mouse likes piquant cheese. And here we have the linearized AMR. We see already that it's not so pleasant for the eye to understand. But we have also the multiline indented penman structure, which is already a bit more clear, and it's nicer to watch at it with our eyes because it provides some additional structure. And we can, if we use a 2x2 convolutional kernel, we could capture that the mouse likes cheese. If we use a 3x3 convolutional kernel, we could already capture that like is the arg1 of possible and the mouse likes cheese. And if we use a larger kernel of 4x4, we can even capture some greater structures like the mouse likes piquant cheese. And note that in this linearized AMR representation, piquant and like, it's like 9 hops or so, but here we can capture it all with a single convolution. So here's an intermediate conclusion. By using AMR as image, we can use a simple CNN as an encoder for AMR graphs, and of course also for the dependency graphs, because they also can be represented in the simple penman format. And all this while preserving all vital graph structure. And here are our experiments for estimating AMR quality. we have some baseline models, a ridge regressor, which uses some shallow graph statistics, for example, the difference in the degree of the dependency tree and the degree of the AMR graph, or the difference in the amount of nodes of the dependency tree and the amount of nodes in the AMR graph, and so on. Then we have a baseline graph neural network, standard graph encoder, and we perform regression based on the joint average vector from dependency node embeddings and AMR node embeddings. And then we have a linearized graph LSTM from previous work, which uses the linearized graph representation and encodes it with LSTM, but also uses some extra features such as a shallow alignment from the dependency tree to AMR. And keep in mind, all what we use is a very standard vanilla CNN. First, we use some 3x3 kernels to capture more local graph structure, and then we use on top of that some larger kernels to capture the more global structures. But all a very simple CNN. And here are our results. This is the correlation with the gold scores, and we see that our simple convolutional neural network outperforms the best baseline in estimated SMATch F1 by 3 points, in estimated SMATch precision by 2 points, and in estimated SMATch recall by 4 points. We can also predict more AMR quality, more fine-grained AMR quality dimensions, and here we see that our model produces better estimations of frame quality, both for labeled for predicates with labeled senses and for predicates without senses, and for the estimation of coreference quality we also improved by 18% relative change. We also perform another experiment that is classifying graphs into quality categories. We have 5 categories. The graph is of poor quality, of mediocre quality, of good quality, very good quality, and excellent quality. And here is the result. First, we have the macro F1 score, and we improve upon the baseline by 4 points. And because this is a classification of a nominal scale, the macro F1 score does not really reflect the performance of a classifier well. We also use the quadratic kappa, which takes into account that it's a nominal scale. And in the quadratic kappa, we improve by 7 points. But what's really cool about the model, it's because we've used such a simple convolutional neural network, we massively reduce the training cost. We see here that we improve the time per epoch massively, and we reduce the kilowatts per hour, the kilowatt hours per epoch also massively. The only downside is that while training the baseline model I can drink lots of coffee, and while drinking the CNN model I can only drink a short espresso. Here are the conclusions of the work. We preserve vital graph structure by treating AMR as image with latent channels. This representation allows spatial interpretation of AMR graphs motivated by AMR annotators. It facilitates processing with simple CNNs. The model outperforms strong baselines in AMR quality rating, and the model has low energy consumption and fast training time. Here are some possible directions for future work. We could improve the simple CNN by incorporating attention mechanism. We could improve the CNN by investigating better kernel sizes. We could aim at generating finer predictions. For example, directly we could predict whether a specific node or edge is redundant, missing, correct, or false. We could improve the model by using contextual embeddings. This is pretty straightforward for the dependency tree image representation, since we can just use the token embeddings from the sentence as latent channels in the dependency image. But it's not so clear how to do this for the AMR graph, since the AMR nodes and edges are often abstract. It's not really clear how to generate contextual embeddings by using like BERT or something. Thank you for your attention.